the Omni factory generator and then try running it and verifying that you can get the logging output for each factory, for your new factory, and that if you add it to output includes collections, it gets called all the time. And I encourage you to do that later on your own time or immediately after this. And if it doesn't work, we can work on it together. All right, moving on to the next part, parameterizing a factory. So parameters are also handled using our registered members. We provide this parameter class template. We also provide this parameter ref class template. And the reason we use this parameter ref class template instead of the parameter class template is because we're also using these config objects. And the config object is just a plain old struct that holds data, and we'll talk about that next, but you can just think of it as being, you're storing the configuration for the factory outside the factory itself. I'll explain why later. But so you can just declare a parameter ref, you declare what type it is, you give it a name, you register it with the parent class, you give it a parameter name, and this parameter name is something that you can specify in a config file or on the command line. But note that it is namespaced. So you use the tag name for the factory to namespace the parameters. And then this is a reference to the place where the parameter's value actually lives. Again, this is a parameter ref, so the parameter value doesn't live inside the parameter ref, it lives in this other weird place, so we have to provide that. If we didn't have a parameter ref, if we just had a parameter, then you wouldn't need this config object, and then the parameter value would just live inside this parameter object, kind of like our collections. And again, so parameters are fetched immediately before the init callback gets called. So that means that in your process, for instance, you can just say, hey, I need my sampling fraction parameter. And once again, you're using this operator call syntax, which is, makes it look like a function, even though it isn't really a function. And then all this goes into the logger so that you can observe the parameter that you're trying to set up. Now, you might be thinking, why do we bother going through this sampling fraction if we already have it as a field on this config object? And you're absolutely right. So we don't need to go through this. We can just go and access it directly from the config object because it's been set up like that. And if you're using your algorithm, eventually you won't have access to this. So this is the way to really do it. You might ask, well, why do we need this sampling fraction, to have a name at all if we can access it this other way? And the answer is we don't really need that either. And in a future version, we'll be able to sort of anonymously declare these parameter refs. But for now, you just declare a bunch of these, and that sort of binds the config object to the parameters that you can get from the parameter manager. Let's talk about our config objects a little bit.
One sec.
Yes.
I see Saqib has raised his hands.
Oh, Saqib.
I think he's going into the discussion. I was going to ask how the config objects are defined. So that's okay.
Yeah, it's a little bit weird, like which to show first. And I don't think I'm quite, got it. So that might be improved. But the like the concept of the parameters is a higher level concept than the config objects, and it's more fundamental. And the config objects are sort of controversial anyhow. But config objects, it's literally just a plain old structure. We give it a fun name like reconstruct electrons config. For now, we have to put this config struct in the same header file as our factory or in a separate file, which they do. I think it's a little bit overkill personally, but you can do that. Ultimately, the config struct is something that the algorithm is going to need. And, the factory knows about the algorithm and the algorithm doesn't know about the factory. So really the config struct should live with the algorithm. But for now, we'll just put it in the same header file as the factory. And it just contains a bunch of parameters. And we can give them default values, which is cool. And by giving them default values in the config struct, that means you don't have to, assign every single value in the factory generator level. So you sort of have several levels of defaults for your parameters. The values in the config struct are like the most fundamental values. Those can be overridden by the Omni factory generator. And then the Omni factory generator can be overridden by the config file or by the command line parameters.
One second, and I understand why you as a non-physicist might do this, but it's important to point out to new users, always use units. I don't know what a threshold of 0.9 is. Unless this is E over P. If it's really just for E over P, then that is a number.
No, that's a great catch, and I'm glad you said that. And we should absolutely put units on everything. I 100% agree. I just came up with names of plausible sounding parameters here. This isn't meant to be the one true set of parameters for reconstructed electrons. And in fact, when you see the final example, you'll see that it's not at all. But
yeah,
yes.
no, it's a general comment because I just went through one config file in a completely different factory, and I found pretty much exactly time resolution equal to 0.8.
So I like putting the units in the variable name, honestly. So, threshold.
No, the recommended, I mean, that makes sense too, but the recommended way is to really just multiply it by DD4HAP : nanosecond, NS or GeV or something like that. I think there are multiple namespaces that provide the same thing because it could also be CLHAP because they're the same thing. And I think EDM for EIC also offers a nanosecond. They're all the same.
Well, mostly all the same. Wasn't there one package that, gave everything in like centimeters instead of millimeters or something?
Yeah, that happens. But I'm saying the units are provided by multiple namespaces.
Oh yeah, no, absolutely. And if we're using the convention of like always using the DD for HEP, unit multipliers, by all means do that. I don't have that luxury because Jana doesn't have a particular library that provides units. Units we care about aren't really units physicists care about, because if we're encoding physics domain knowledge in the framework, that's a bad sign. But units. All right, so reconstructed electrons factory. We have this config method, which lives on the Omni factory, which lets us access this config object. But we still have to tell, oh, this is a bug. This should be underscore lowercase config. Sorry about that. But we have this additional optional template parameter for this is the type of config object that our Omni factory needs. And so once you know what your Omni factory config object should be, once you've created one, then you just pass it in as another template argument to the Omni factory. And then the Omni factory generator knows what to do with it. So by saying an Omni factory generator T of type basic test alg has this config T type now. You can now pass a anonymous config T directly to your test alg from your generator and provide it with whatever values you didn't have in the thing above. All right. And then this brings us to overriding parameters via the command line. So like I said, we have several levels of defaults. We have EIC. Now we can just pass this as another parameter using -p. And then you notice our tag is fun test. So here we're saying fun test : threshold. And then that will override whatever we specified here, which in turn overrides whatever we specified here. All right, I'm just going to briefly mention services. There's not much to mention about them. Usually we need DD for HEP in EIC recon. The way we obtain DD4HEP from Jana is by just saying, hey, we need this service. It is of type DD4HEP service, and stick it in this MGO service handle. And then just like with parameters and inputs, you then use this function call operator to get the service out of the MGO service. And the exercises that I would want you to do if we had the time would be to give your factory this config struct and some parameters, and then experiment with overriding the parameters different ways. Any questions before I move on?
This -p stands for parameter.
Yeah.
This is overriding.
Yeah, so
so
it's just we're passing in the parameter, and it's name equals value, and then we just parse it as a string, turn it into whatever.
As a comma separated, if say I want to pass more than one parameter in the bash line.
Yes,
Okay.
comma separated. Occasionally, there's other parameters in Jana, particularly paths, that we colon separate, but for parameters and for most things, we always comma separate them. Oh, actually, hang on. You can also just do this -p separately, so it isn't just one parameter. So you can be like -p Jana n events equals whatever space -p whatever. Sorry, we use the commas more for lists. So if you have a parameter that's a list of things, we use the comma for that. Yeah, so each parameter gets its own -p, to be clear. All right, well, I'm going to move on to the algorithms, since this whole talk is supposed to be about algorithms. So we already talked about factories and talked about how factories do all this plumbing, and we can attach all the things we need between the, the different interface that we have for EIC Recon. We give it all the way to the factory, and then the factory is sort of in charge of running this algorithm. And the algorithm is supposed to be clean and neat and independent. And essentially what an algorithm is just a method called execute that takes some pod.io collections and returns some other pod.io collections. It also has that same config structure that the factory has. And then the goal is to keep it simple. Now, when I say keep it simple, it's worth pointing out that there is an effort to try to make the algorithm's interface a little bit richer and a little bit more declarative. So the idea is that if you can put all of your inputs into the type system using these fun variadic parameter packs, then you might be able to do this a lot more generically. So you might be able eventually to say, we're going to have a template that knows how to create a factory simply from the algorithm definition. And this is an ongoing research project, and I think there'll be a discussion about it tomorrow. But the idea there is to just formalize algorithms a little bit more. Now, this formalism, it lives in a separate repository. If you look at the EIC Recon code, you'll see that some people are using it kind of experimentally. It's a work in progress, so I'm not encouraging new users to use it. So for instance, like it's changed quite a bit since I've last seen it. I don't even know what its status is right now. But there is an effort to make it more formal. All right, so where do we put the algorithm code? Under source algorithms. That is the answer. The basic algorithm interface. Here is what you would want your algorithm to look like. So you have an init function, you have an execute function. One important thing to point out is that the return types need to be unique pointers so that we can give them back to pod.io, and I'll explain why a little bit later. And also that we need to sort of pass all of our services from the factory to the algorithm itself. So the algorithm also needs the services. But this is really just like a very simple convention that we follow. And then this is what it looks like to call an algorithm from a factory. So in the configure, you generally need to actually create the algorithm object to begin with. We're using unique pointers for that as well, just as a matter of convention. And then we need to pass the config object from the factory to the algorithm. So we do that here. And then we need to initialize the algorithm and pass it any services that it needs. And in this case, all it needs is a logger. So we pass it the logger. And then from our process method, we have this algorithm execute method that we call. And we can just pass the pod.io input collections. And again, we're passing the output back as a unique pointer, which means we can just standard move it into the output. Now, one question you might have is what happens if you have multiple outputs? And the answer is you can use a standard tuple for that. So you can have as many outputs as you want. And then you just unpack that tuple and assign it, each item in the tuple to one of the output collections you have specified here. I think this is a good place to ask if anyone has any questions.
Can I ask generally, for my understanding? So these factors and algorithms can run in parallel, but what if I need something to be in sequence? How can IRC recognize it?
So if you have something that needs to be run in sequence, it probably shouldn't be, it shouldn't be in a factory to begin with. So the intermediate objects, generally those should be, generally you should be writing algorithms that aren't storing global state inside of them to begin with. Like it's always possible for you to go and to, acquire a lock if you have an algorithm that does have state inside of it that needs to be protected. But we're really trying not to do that.
Yeah, because of multi-threading, I see.
Now, so what are you supposed to do if you have something that absolutely has to be sequential? And the answer is one of two things. Either it should be a service or it should be a JEvent processor. And those are very different things. So I'll drill down to this a little bit more. One thing we need is to retrieve like calibrations from a calibration database. And that absolutely has to be done sequentially because the calibration database, it's a shared resource. But you're doing that through a service, and then the service has to be thread safe. So that's the first part. And then that is why, factories have all this caching of calibration and resource data, is because you don't want to be acquiring that lock at all if you can help it. And if you do it the minimum number of times possible. So services are one place that you put things that are sequential. And the other place where you'd put them is the JEvent processor. And processors are when you have things that sort of look like an output. That's also for things that look like they need the entire event stream. So for instance, if you want to say, just show me all of my reconstructed electrons that I've produced anywhere from all my events, maybe put them in a histogram, whatever, that's something you'd put in a JEvent processor. Another thing is, what if you want like an event display? An event display, it could have some fancy front end, which is completely separate, or it could be the standard root front end. But either way, the way that the event display would talk to Jana is again through an event processor. And the event processor, it can have locks. And we have some pretty fun mechanisms for, having sort of higher level locks. So you can have multiple event processors that know they can't run at the same time as other event processors, but not all event processors. So like you have like this global root lock, for instance. So anything that needs a root can all go down to that same lock, but everything else doesn't. But again, like this is a very specific use case for the sequential stuff. All right, did that answer your question?
Yeah, I think it did.
Great. All right. So while I'm still on this particular page, I'm just going to say we have this configure and we have this process, and you can sort of see a pattern, and there is some potential in the future for this being something that could be automatically generated using a very complicated template, but that is not there yet. So pretty much you get to be that template. But the good news is it's a pretty easy thing to do. And if you had time, then the exercise would be to try to create this basic algorithm using that code skeleton. And like, don't have the algorithm do anything, just, be able to show that the factory can call the algorithm and you can see a log message coming from execute. All right. And now in the last 6 minutes, I can move on to going deep inside the algorithm. And this is, how do we work with pod.io? And so pod.io is another framework. It's a library that generates a data model for us. And we can define it in one place using YAML. And this is sort of the simplest possible data model you have, where you have just a hit and a cluster. You can already see that you have different fields on the these data types, and they have types and they have descriptions. Also notice that you can have one-to-one relations and one-to-many relations between these objects. And then pod.io sort of manages this for us. pod.io generates a lot of different classes, and it has many different moving pieces. And it has this sort of layered architecture. And the reason for that is because it manages memory in a very precise and sophisticated way. And it means that you don't have to worry about deleting pod.io objects. Instead, it moves them behind the scenes for you. So you can have a pod.io object reference wrapper that you work with, and pod.io's keeps the data somewhere else that you don't get to access it directly. And this means that the code for working with pod.io and C++ looks a lot more like the code in Python and other garbage collected languages. So there's the memory layout that pod.io uses is completely hidden from the user. And then pod.io has this strong concept of immutability. So you can create data, and while you're creating it, it's mutable. In fact, you even have like this mutable data type, which is different than the regular data type. But once you give that mutable data type to your collection, it becomes immutable. And then that data is now sort of set in stone, and it's permanently a part of that collection just the way it is, which means that you have this sort of integrity of all of your references. And that means that you can be confident that, this data was written in exactly one place in EIC Recon. So you can go to that exact algorithm and know that it hasn't been messed with by somebody else. All right, so this means that there's entire classes of bugs we don't need to worry about, but there's still some subtleties. In C++, it's not perfectly safe no matter what. But this is a general example of how you would go about using pod.io, where you can create a collection, and then you can create hits and immediately pass the hits, push them back into the collection. If you need to build it up in little pieces, then you can do so. by creating a new, notice this is example hit and you're passing all the values already created. So this is immutable and you can't change any values on this. But this one is mutable, so you can set and reset and do whatever you want with them right up until you push it back into the hits collection. And then the other thing that you should be aware of is there's this concept of subset collections, and subset collections is a weird way of saying we're not actually creating new objects. We're just referencing objects that already belong to another collection. And that way you can say something like, oh, we're going to filter all of these clusters and only keep these ones. And we're going to have a separate collection containing the filtered, clusters, but that one is very lightweight. Like we're not going to copy all of the data. We're going to save ourselves some trouble. And so the goal for this little part was to just produce some fake output data. And then for the final section, for the reconstruction algorithms, we just have...
Nathan, sorry, can I just ask a question? Because so we don't have time to go through like since we can't run the examples in real time,
Right.
these exercises, will you have anything like posted for people as they work through it? Like an example, like, I don't know.
Like you read my mind.
Like
or I
the
read your mind.
solution. Oh,
The
okay.
entire solution is on the last slide. So you can...
Yay, okay, you're building to it. Got it.
Yes. And this has the actual logic in it as well. But if you follow the directions here and you run into trouble, you can always cheat and look at the final slide. And that's it. We're at 11:29 and it's been a long day for you guys, I'm sure. So I'm just ready to answer questions or help you debug as you see fit.
Let's start by saying it's been probably a long 2 hours and change for you as well. Thank you very much.
Well, thank you for putting up with all my tech problems.
I guess, does anybody in the room have any questions before we close out? Too many. Okay, he has too many. Yeah. Okay. So again, like I think as questions pop up, because people have been asking too for some of the other tutorials as they work through things and run into problems, because we'll make the recordings and of course the material's already been posted. But if people work through things and run into problems, I'm encouraging people to post on the Mattermost tutorials channel. So if that works for you, Nathan, as a place to respond to people there as well, then we have it kind of documented, at least when people are
Absolutely
asking these questions. Okay, very good.
Oh, and I mean, don't spend hours on it, but if you could go through the material and maybe remove or fix some of the little problems that we had along the way.
Yeah.
Like some of the typos, that kind of stuff.
Yeah, there's like 3 or 4 things that I took notes about while I was doing this.
Awesome.
Okay, let's see. Does anybody online have anything they want to ask before we close everything out?
I actually had a question, maybe not related to the tutorials, but is there a way to figure out, if you add like a new factory or a new algorithm, how much like memory it's using, like in terms of like profiling any new addition, like?
So memory is a little bit harder because you can't really get that information without really hacking at the allocator. We don't have a way to hack the pod.io allocator from factories. So for memory specifically, I'd say you're better off just using, off-the-shelf profiling tools. That being said, you can always see exactly how many objects of each type and then multiply that by the size of the object in principle to get a sense of how many intermediate objects are being created at each step. Although I don't think that's really what you're asking for.
Yeah, I was just, yeah, I think like the point that you made about just using a generic profiler. I was just trying to see if there was an easy way to say, if I add a new component, if it's like really degrading the performance of EIC Recon in terms of like memory. and know it. Yeah.
This is something that drives me nuts about, C++ compared to something like Java, where you can have these lovely memory maps that you can actually look at, and I miss it. And I was hoping that there would be a good way I could at least, observe how much memory, is being used, from EIC Recon itself, and maybe use that to, change how Jana is running, for instance. But it turns out
Sakib, can you send me an email and CC Nathan? I have dirty, quick, not great code, but it works to at least see your resident memory in a single threaded application, what have you. It's all very restricted, but maybe that helps a little bit.
With a nice time display that shows you how long everything's taken. It's taking 95% of the computation time. That's been heard at the end of running EICB.
At the end of running EAC Recon, it does spit out this nice table of which algorithms have taken up the most time. So if you're adding a new thing and it shows that it uses 95% of the time, you'll probably get shouted at by someone.
absolutely.
Sorry?
You can shout at yourself when you run your own job.
Yeah, but if you haven't noticed and someone else picks up on the fact that you're looping over something millions of times when you shouldn't be, then someone else will pick up on that. I don't know if you've got an example of the output of the EAC Recon still up there.
Yeah. So
On
it's
the
the Jana.dot files what you're talking about. And we do have visualization tools for this, but you can also just use GraphViz, like that's where the format actually comes from. Of course, will it let me, hang on. So if we open the Jana.dot, oh, look, it even generates SVGs for us automatically. Beautiful. Oh, that might be a mistake. So this is going to be a very complicated SVG when it loads. Come on. All right, well, anyhow, yes. So the Jana dot gives the entire call graph, and it gives performance information at every level in the call graph. So you can see exactly where you're spending all of your time.
Okay, very nice.
Any other questions? Okay, I don't see any, I don't hear anybody piping up. So I guess I just want to thank everybody who stayed with us all the way through at the end. These recordings will be up hopefully by the end of the week. I'm just going to drop a link in the chat. So anybody, I'll send this out in an email when I post the recordings to let you know it's there, but just anybody that can just fill out